What specific problem does your method aim to solve in the context of visual language models, VLMs, particularly regarding dataset limitations and training efficiency?
Our method specifically aims to address the limitations of human-generated datasets and the simplicity of tasks in training visual language models, VLMs. We recognize that existing datasets often consist of coarse-quality image-text pairs, which can hinder the performance of VLMs due to their lack of detail and depth. To remedy this, our approach utilizes the VLM itself to iteratively refine and augment pre-training data, enhancing the quality of captions through a self-augmenting loop. This process not only improves the richness of the training data, but also reduces the reliance on costly human labor or proprietary APIs for generating detailed captions. Ultimately, our method enhances training efficiency by leveraging the VLM's capabilities to produce high-quality, informative captions, thereby boosting model performance across various benchmarks.
Can you explain the main steps of your proposed training regime, particularly the self-augment step and the specialist-augment step, detailing how they interact with each other?
The proposed training regime consists of two main steps, the self-augment step and the specialist-augment step. In the self-augment step, we initiate a bootstrapped loop where the initial version of the VLM, referred to as VILA_0, generates enhanced captions for the pre-training dataset, significantly increasing the quality and detail of the captions over several iterations. This process continues until performance improvements saturate, typically after 3 rounds, where the generated captions become longer and more informative, reducing hallucinations. Following this, the specialist-augment step introduces task-specific knowledge by fine-tuning specialist VLMs, which focus on specific tasks such as spatial awareness, OCR, and grounding. These specialists recaption the pre-training data, and the self-augmented VLM is then retrained on this newly recaptioned data, allowing the two steps to interact synergistically, enhancing the overall model performance by leveraging both general and specialized knowledge.
What are the key advantages of using your VILA$² approach compared to traditional methods in terms of dataset quality and model performance?
The VILA² approach offers significant advantages over traditional methods by enhancing dataset quality through a self-augmenting process that generates longer and more informative captions, which improves the overall training data without relying on costly human labor or proprietary APIs. This iterative self-augmentation leads to a substantial increase in caption length and detail, as evidenced by the transition from brief original captions to enriched descriptions that cover visual semantics more comprehensively. Additionally, the incorporation of specialist VLMs allows for task-specific knowledge to be integrated into the training process, further refining the dataset and boosting model performance across various benchmarks. The synergy between self-augmented data and specialist knowledge results in a notable performance improvement, as VILA² consistently outperforms state-of-the-art methods on the MMMU benchmark. Overall, VILA² not only enhances the quality of the training dataset, but also pushes the performance boundaries of visual language models significantly.
Describe the experimental setup and metrics you used to validate your method. How did you ensure the reliability of your results?
In our experimental setup, we followed a 3-stage training paradigm consisting of alignment, pre-training, and supervised fine-tuning, SFT, using various model architectures, including Llama 2-7B for exploratory experiments and Llama 3-8B Instruct for state-of-the-art comparisons. We utilized a diverse dataset blend, including 6M sampled MMC4 and 25M sampled COIO, ensuring a fair comparison by only replacing text captions while keeping image sources constant. To validate our method, we employed common VLM benchmarks such as VQA, Science QA, and Text VQA, and conducted ablation studies to assess the performance of different iterations of our VILA models, specifically comparing VILA_I across multiple rounds of self-augmentation. We ensured the reliability of our results by integrating high-quality image captioning datasets and diverse instruction fine-tuning datasets, which allowed us to maintain narrative and instruction-following abilities while acquiring task-specific knowledge. Additionally, we observed consistent performance improvements across benchmarks, confirming the effectiveness of our self-augmentation and specialist-augmentation strategies, as detailed in our results section.
What specific improvements in performance did you observe across different benchmarks after implementing your augmentation methods, and what were some key examples that illustrate these improvements?
After implementing our augmentation methods, we observed notable performance improvements across various benchmarks, particularly in VQA tasks. For instance, the self-augmentation process led to a significant increase in caption length and quality, with the average number of words growing from 12 to 101 after the first round, which correlated with improved benchmark scores. Specifically, VILA_3, which incorporated a spatial relations understanding specialist, demonstrated enhanced performance by providing more detailed and accurate descriptions of spatial information, surpassing the results of the previous rounds. Additionally, the integration of multi-round QA pairs from all three specialists resulted in significant improvements across 5 out of 8 benchmarks, showcasing the effectiveness of our approach. Overall, VILA2 achieved state-of-the-art performance on the MMMU benchmark, highlighting the success of our augmentation strategies in refining dataset quality and model capabilities.
Discuss any trade-offs or limitations of your approach, particularly in terms of computational resources or the nature of synthetic data utilized in your training process.
Our approach, while innovative, does present several trade-offs and limitations, particularly regarding computational resources and the nature of synthetic data. Firstly, the self-augmentation process requires significant computational power, as we utilized 128 GPS with a global batch size of 1024 during training, which may not be feasible for all researchers or institutions. Additionally, while our method improves caption quality through iterative self-augmentation, we observed diminishing returns after 3 rounds, indicating that excessive reliance on synthetic data can lead to saturation in performance gains. Furthermore, the synthetic captions generated by VILA may introduce hallucinations or inaccuracies, which we attempted to mitigate through careful prompt design and the integration of original human text. However, this reliance on synthetic data raises concerns about the potential biases and limitations inherent in the models used for caption generation. Lastly, our approach primarily focuses on enhancing the quality of existing datasets rather than expanding the diversity of training data, which could limit the generalizability of the models to unseen tasks or domains.